So, all right. Today we start compactness. Compactness is one of the major actually concepts in analysis. This is actually a big step, in mathematics learning. Uh, it's like learning epsilon delta arguments or limit definition. Uh, you should consider this, as a major thing in actually, mathematics education, compactness. I'll give the definition and spend some time on definition. We will see it over and over. Try to learn the definition in detail, why it is important and so on. You should pay some attention. Later you will see why this definition is actually so important, and you will appreciate that. Okay, so let's start with the definition. First, let E be a subset of a metric space a collection of open sets. Let's say this collection is OIs. I belongs to some index set, so we have some collection. It can be finite, infinite, countable, uncountable, any collection of open sets in X. So each OI is an open set in X, is called an open cover for E. If what happens? If E is a subset of the union of these OIs, okay? So if these OIs cover the whole subset E, then we just call this an open cover for E, okay? An open cover for E. All right. What is compactness? Okay. So a subset E of X is called compact. In Turkish we say tıkız. A tıkız subset uh, is called compact if what happens? If any open cover O alpha of E has a finite subcover. What does this mean? Let's write down. Open cover means, so E is a subset of the union of a collection of open sets. Each OI in X is open for all I. This should imply the following. E is lies in the union of finitely many of these. for some I1, Ik in the index set. Which finite open sets we don't know, but there should be some, OI1, OI2 in this open cover so that they cover the whole set E. Okay, we call in this case E a compact subset. So this should hold for all open covers. Okay, whenever you give me an open cover, I should be able to find finitely many elements of that open cover which covers the whole subset E. If I can do this for any open cover of E, then we call E a compact subset. All right. Any questions so far? I'll do some examples, but if there's something you don't understand, please stop me. Some examples. First of all, any finite set is compact. Any finite subset E is compact in any metric space. Why is that? Let's see the proof. So let E, for example, be this x1 up to xk, a finite subset. To show this is compact, I need to take any open cover. So let OI be any open cover. Okay. Be any open cover for E. Well, this means what? Hence, this E, which is consisting of finitely many elements, lies inside the union of these open subsets. Well, my aim is to pick up finitely many OIs that covers still E. Alright, this is very easy now. Why is that? Because you see, x1 is an element here, but it certainly lies inside one of them, right? Since xi belongs to this union, there is some index I1. Alright, let me say maybe xj. Ij. Maybe I should start with x1. There is some I1 in this index set so that x1 is in OI1, right? The first element is inside one of them. Similarly, x2, x3 will be in some x2 is in OI2 and x3 is in OI3 for some I1, I2, I3 in the index set. All right. So this way we find I1 up to Ik in the index set so that xj lies in Oij, j from 1 up to k. Okay. So for each xi, I picked one open subset. Since there are only finitely many elements in the set E, finitely many open sets will do the job. Now E, which is just x1, xk, will be inside OI1. x1 is in the first open set, x2 is in the second open set, and xk is in the kth open set. So what I did, I started with an open cover, right? I started with an open cover for E. So I have this. And I could choose finitely many open sets which covers E. So we are done. Hence E is open. Okay. Sorry. E is compact. All right. Another example. This was a finite set. Now let's see another example, which is an infinite set this time. So let E be this expression 1 over n's, and from 1 up to infinity. Okay. And I include also infinite. Okay. And consider this as a subset of real numbers with absolute value metric. So we claim that E is compact. Okay, E is compact. Let's see the proof. So let OI be an open cover for E. The idea is this. Let me give you the idea first. What is this E? This E is this subset. Here is 1, here is 0, and E consists of this elements 1 over 2, and then 1 over 3, 1 over 4, and so on. And here's 1 over n, and so on. I should be able to pick up finitely many OIs which covers all these, elements. How can I do this? Well, the idea is this. You see, one of them contains 0, because you see I have this inclusion, right? E is a subset of this OIs. So 0 belongs to E, therefore 0 belongs to one of them. Since 0 belongs to one of them, there is an open, and whatever that element is open, there is some interval in E which covers that element and lies in this open set. So there is some interval like this, such that this interval lies inside one of these open sets. But you see, if there is an element like this, then we know that since this sequence 1 over n converges to 0, after some index on, all the elements of this sequence 1 over n's will lie inside this interval. And that interval will lie in one of these open sets. But you see, then there will be only finitely many elements left outside, and each one, as in the above example, will lie inside one of the open sets. So those finitely many elements will be contained in finitely many OIs, and the rest, which is infinitely many, which contains infinitely many 1 over n's and 0, will lie inside one of them, just one element. So in total, the whole subset E will lie inside only finitely many open sets. So that's the idea. Now let's write it down. Okay. Now since 0 is in E and E lies in this union, there is some I0 so that 0 is in EI0. But not E, sorry, OI0. This is an open set. Since OI0 is open, there is some R positive, so that uh, 0 belongs to the interval 0 minus R, 0 plus R, and that interval lies inside OI0, right? Maybe I should just write this minus R plus R. Yeah. Now, then we observe the following. The sequence 1 over n has limit 0. In other words, we have this limit 1 over n is 0, and hence hence there is some n0 natural number, so that n greater than n0 implies 1 over n lies inside the limit in this interval 0 L minus R, L plus R. So what we see is this then 1 over n0, 1 over n0 plus 1, 1 over n0 plus 2. All these elements are in this interval. And this interval already is in one of the open sets. My aim is to find finitely many open sets in this collection of OIs, right? In this collection that covers all of them. I found one open set which covers almost all of them, right? It covers all the elements after the index n0. Well, how many elements left out? The first n0 minus 1 terms. Now I'll pick one open set for each of them. Now for the remaining terms, which elements? 1, 1 over 2, 1 over n0 minus 1. Pick open sets OI1, OI2, OI, which so n0 minus 1, so that 1 is in OI1, 1 over 2 is in OI2, and 1 over n0 minus 1 is in OI n0 minus 1. So you see, I found finitely many open sets which covers the elements 1, 2, and 1 over n0 minus 1. And the rest lies inside just one element, OI0. So I am done. Now, E, which is 1 over n's, and from 1 up to infinity, and 0 lies inside which collection? Uh, Infinity many of them lies in OI0, and the rest, so 1 lies in OI1, 1 over 2 lies in OI2, and I have just finitely many such elements, OI and 0 minus 1. So what we have done, we found, given this collection, okay, I was given this. E is a subset of uh, this open subsets, and I found finitely many open sets, this one, this one, this one, and this one, and 0 of them, which contains whole E. Hence, E is a compact subset of E. Sorry. This metric space of real numbers with the absolute value metric. All right. Any questions so far? I should here say as a remark, the proof I gave should work as any metric space, for any metric space. So let me just leave this as an exercise. So let xn be a convergent sequence in any metric space with limit xn is equal to, let's say, x0. Okay. Then the subset, which subset E, which I take xn's and from 1 up to infinity. So I take all the elements of the set, union the limit point, okay, limit point. Then this is a compact subset, is a compact subset of xd, okay. The proof is the same, as above. So just mimicking that proof, you can prove this. All right. Well, I gave two examples. Now, two non-examples. So the metric space, so the subset E, which is R itself. Yes. Yok. Yani şey doğru değil. Mesela sadece bir bölenleri alırsan o doğru değil. I'll do that. Okay. So it will be my next example. So first, this subset is not compact in R infinite. And my second example will be that element, actually subset, the one you mentioned, which is a bounded set. Why this is not compact? Well, to show that something is not compact, you have to show that the definition of compactness is not satisfied. This means what? You have to construct an open cover which do not have any finite subcover. Well, for R this is kind of easy. Why is that? You see, here is R. I can cover the set of real numbers by open sets like this. First open set, the second open set, the third open set, and so on. The nth open set, which is minus n, minus n. And you see, finitely many of them will never cover the whole real line. Therefore, E is not compact, okay? So, you see, let On to be minus n plus n being a positive integer 1, 2, 3, and so on. Clearly, the set of real numbers is inside, right? So this is in this union, it's equal to this union, so it's in this union and from 1 to infinity, and R is not inside this collection if you choose only finitely many of them. So it's not in n1 and let's say k and k for any n1 and k. Why is that? Because these are intervals, one inside the other one, because of this. This union n1 and k is equal to what? This is just minus n0 n0, where n0 is the maximum of n1 up to nk, right? If you choose n0 to be the maximum of these open sets, indices, then the union is equal to this open set, and clearly R cannot be a subset of this, finite radius open set. So R cannot be contained in the union of finitely many ONs. Therefore, this open cover, hence the open cover ONs has no finite subcover. Okay. So R is not compact. It's not a compact subset of what? Okay. Another non-example is the example your friend mentioned. So let E be this set. For example, let's just take this one, 0 and 1. Okay. Again, in the standard metric space are uh, equipped with the absolute value metric. So what is this interval? This interval is the interval containing 1 but not containing 0. So this is not compact. Again, why is that? So claim is, so it's a bounded set. It is not compact. Again, I have to exhibit a collection of open sets which contains E, so that no finitely many elements from that collection will cover E. Okay. All right. How can I do this? Well, this is what I will do. So proof. Just let ON to be this. 1 over N and then 1. Okay. Well, you see, my open set is this. If you pick any element here, X, in this E, since 1 over N has limit 0, after some index, 1 over N will be somewhere here. Right? For each X, I can find such an element which is smaller than X. So this X will lie inside that element 1 over N. Therefore, this interval, okay, since for any X larger than 0, there is some N0, there is some N with N larger than 1 over X by the Archimedean property. We see that X is less than 1 over N, and thus X, okay, thus X lies inside this open set. 0, no, 1 over N and 1. Okay. So the interval E, which is 0, 1, lies inside this union. Okay. These are all open subsets of course, 0, 1, right? These are open subsets of 0, 1. Are all open. Maybe I should be more careful. Here, these sets should be open in R, so maybe I just choose this. Okay, yeah. If I take my metric space, the interval 0, 1, then that would be fine, but here I have to be more careful. Okay, these are open sets. But, finitely many of them, however, finitely many intervals like this, so E won't be a subset of finitely many of them. So 1 over n I to I from 1 up to, let's say, k. Okay, for any k and N1, and K. Why is that? Well, you see, you just take intervals 1 over n's. None of them will reach 0. So there will be some x which is even smaller than that. Therefore, finitely many of them will not cover. So the reason is this. This is because the union I from 1 up to k 1 over n i's 2 is equal to what? This is just 1 over n0 2, where n0 is again the maximum of n1 and k. Okay, since there are only finitely many of these, if I am given finitely many of these, I can always find the maximum, and these intervals have union equal to this one, and this interval clearly doesn't contain 0, 1, and 0, 1 is not contained in this union. Because there's always some real number which is less than 1 over n0. Okay. All right. So we have seen some examples of closed sets, compact sets, and some examples of non-compact sets. Here you see this is not compact since it doesn't contain 0, and 0 is the limit point of a sequence which lies inside this set. Okay, so this means a compact subset maybe must be a closed subset. That is true. Actually, there is more than that. It is not only it must be a closed subset, but actually it must be an complete space. Okay, I could repeat this kind of argument for any Cauchy sequence, and if the Cauchy sequence doesn't have its limit in the set E, this argument would again tell us that E wouldn't be compact. And this example shows what? R is not compact because it is not bounded. Right here, I just take larger and larger intervals to cover E, and therefore finitely many of them won't be enough to cover E. So a compact subset must be first bounded and complete. Okay, so, and that's my actually first theorem. Okay, so a compact subset E of xt is closed and bounded. I'll take care of completeness later. Why is that? Proof is just simple. I'll just consider the above examples actually. That will be enough. For boundedness, okay, if it is not bounded, then it means what? E cannot lie inside a ball of finite radius. So if I take a ball with radius 1, E won't be a subset of that. If I take another ball with radius, say 2, again E won't be a subset of that, and so on. I'll take this sequence of balls with increasing radius. None of them will cover E, but these are just concentric balls. Therefore, finitely many of them won't be enough to cover E. So, first let's prove this. Suppose E is not bounded. I assume that it is not bounded. I will arrive at a contradiction. Choose any element x0 in X in the metric space and consider the balls, let me say OI. So ball with radius x0 and center x0 and radius I. Okay, I from 1 up to infinity. Since E is not bounded, none of them will cover E. Okay, since E is not bounded, E won't be a subset of these OIs for any I. Hence, right, these are concentric balls like this one. One of them is this, the other one is this. Okay, with increasing radius. Finitely many of them will not cover A. Hence, A is not covered by finitely many OIs. Excuse me. Okay, so let me write this finitely many OIs. But you see, E is a subset of X, and clearly X is a subset of these balls I from 1 to infinity, because any element in X has a finite distance to x0. Therefore, any element lies inside one of these balls. So these open sets in particular cover E. However, we just see that finitely many of such balls will not cover E. Okay. Hence, so that this collection I is in N is an open cover for E which do not have a finite subcover. So they all together cover everything, they cover E, but finitely many of them will be never enough to cover E. Okay, hence E is not compact. But we started with a compact set, right? E was compact, so this is a contradiction. The reason of the contradiction is this assumption that we assume that E is not bounded. This is a contradiction. This is a contradiction to the assumption that E is compact. Hence, E must be bounded. All right. What was the second claim? Bounded and closed. Okay, let's see. This is closed. Okay, is closed. Oops, sorry. Let's see why this is the true. If it is not closed, again, assume on the contrary that A is not closed. Well, closed, it is not closed means what? There is a sequence in E, it is convergent, but the limit point doesn't lie inside E. Hence, there is a, a, a sequence, convergent sequence xn, so that uh, each xn lies inside E, but limit is not in E. Right? Not closed means exactly this. There's a sequence in E. It is convergent. However, the limit point doesn't belong to E, right? Because a set is closed if and only if it contains all its points in its closure, right? If it is equal to its closure, and the points in the closure are the limits of sequences in E. So if a set is not closed, then it means there is a sequence like this in E. It is convergent, but the limit point is not in E. And then we just do this. Let On to be this open set. X minus the ball with center closed ball x0 and radius 1 over n. It's a closed ball, therefore x minus this ball is open, which is open in X. Sorry. So this is these are all open, which is open in X. For each n. And what is the union of these sets? You see the union of these, and from 1 to infinity. So, and from 1 to infinity, x minus b x0 1 over n. This union is this. This is x minus the intersection of these closed balls. Right? And What is this intersection? I just consider the ball with center x0 and radius 1 over n, and I take their intersection. Well, this is just x minus, this intersection consists of single point x0, okay? And you see x0 was not in E, hence E lies inside x minus x0, which is the union of these open sets, so that this collection O n from 1 to infinity is an open cover for E. But again, those open sets will not cover X. Why is that? It is because of the exercise I gave you, right? You see, there is the sequence xn converging to x0. So if you just take finitely many of these open sets, you know, their union will be will cover everything outside a finite radius ball around this point. But since xn is converging to x0, some terms will enter that ball. Therefore, they won't be inside, you know, in this finite union. So, okay, maybe I do it in the second hour, but that's the idea. Let me stop here for a break. After the break, I'll finish this proof and proceed.